How does the classification of stars help us understand how they evolve over their lifetimes? Let's keep going. Today's question of the day, could you write this down please? How do we determine a star's size and therefore its luminosity? First, let's start by making this in our science journal. Use up an entire page. Maybe it will look something like this. But you're going to have the type of star, its symbol, a couple properties, we'll fill this in today, and an example or two. As an example of a main sequence, write down the sun. The sun's a main sequence star. So we can classify stars based on a lot of different things. Spectral classes are based on their spectrums and their temperature. Luminosity classes are based on how much energy they're putting out, which is directly correlated to how big they are. So luminosity classes oftentimes are another way to describe how large a star might be. And if you take a look at the sun right here, Betelgeuse, this big red one in the background, does not even fit on the screen. Procyon, Sirius, you have a lot of stars much bigger than the sun. And there's even more stars that are much tinier than the sun. The sun's actually like middle of the road. Most stars are red dwarfs, which means most of them are going to be much, much tinier than our sun. As a reminder, spectral class, OBF, GKM, has to do with the temperature. O-class stars are going to be big, but they're also going to be very, very hot. All the way down to M-class stars, tiny and very cool at the surface. Every one of these stars that you see right here is main sequence. So all of these are going to be in the same luminosity class. Luminosity class is basically the size of the star. From hypergiant, most of them are known as giants, down to main sequence, and then we're going to talk about some things past the main sequence. When you guys see these little sections on an HR diagram, and they're labeled white dwarfs, main sequence, giants, supergiants, those names are the luminosity classes. How can we tell which luminosity class a star belongs to? You're probably not going to be able to guess this one, because this is out of left field. It's actually the density of a star. And I just mentioned that luminosity classes have to do with the size of the star, and we'll get to that in a second. But the density is how we place them in the different classes. The higher the Roman numeral, the more dense the star. Let me repeat that. The higher the Roman numeral, the more dense the star. If you guys look above my head, the highest Roman numeral is a 7. That's a white dwarf. The lowest Roman numeral, well, it's a 0. It's not technically a Roman numeral. That's going to be the biggest possible star, all the way up here. The biggest stars are going to be the least dense. So the biggest supergiants are the least dense. They're the most spread out. And the tiniest stars are going to be the most dense, the most compacted together. Higher the Roman numeral, the more dense the star. Please write that down. How can we possibly know the density of a star that is trillions, quadrillions, maybe more miles away? Remember, density is how much stuff there is in a certain volume. How could we possibly measure that? Spectral lines. Let's go back to the spectral lines that we learned with spectroscopy a few weeks ago. Those lines can be very, very skinny. Some of them are going to be a little bit thicker. Some of them can be pretty fat. The size of the spectral lines, the skinniness or fatness of the spectral lines tells us the density. And remember what is making those spectral lines show up. It's light, it's photons that are being absorbed by atoms. So if you have a very skinny line, that means not a lot of photons were absorbed, which means there's not a lot of material out there doing the absorbing. So the thinner lines mean a thinner atmosphere. Thinner the atmosphere, the less dense the star. The less dense, the more spread out it is, which means it's a lower Roman numeral. So let me repeat that. Thin line translates to thin atmosphere. Thin atmosphere is a very spread out star, so it's a very large star. And we're going to give that a low Roman numeral. Conversely, if you have a very thick spectral line, That means that a lot of those photons were absorbed. A thick spectral line means that you have a very dense star, very compact star, because there's a lot of stuff there. So a thick spectral line is going to be a very compact star. The more compact it is, the smaller it is. So those thick spectral lines are going to be a small star. And if you take a look at some of these spectral lines, you will notice some of them are thin, some of them are thick. This is an old version of spectral lines. Let's take a look now at some modern ones. And you'll notice that hydrogen is going to be different thicknesses based on different stars. You're going to get different thicknesses of these spectral lines, and that is going to be able to tell you how spread out the atmosphere is, which then directly translates to how big the star is. One more time. Thinner line, bigger star. Thicker line, smaller star. Is there any way to tell, looking at the spectrums of 3 different stars, blue, green, and red, which one is the biggest? Well, let's zoom in a little bit. You'll notice that the lines that are missing are what was absorbed by the atmosphere of the star. Which one has the most missing? The red one does. So which one has the thickest spectral line? The red one. So which one is the biggest star? Well, if this has the biggest spectral line, it's the smallest star. The biggest star is the most spread out, has the smallest, thinnest spectral lines. So blue is going to be biggest, red is going to be smallest. And if you notice, blue is a 1 Roman numeral, red is a 5, and green is right in the middle. So the lower the Roman numeral, the bigger the star, the smaller the spectral lines. On a test, you're going to get something like this. Which one's the biggest star? What color? Red, green, or blue? Of course, the biggest star has the skinniest spectral line, which would be red. Let me repeat myself for the 300th time. Bigger stars are more spread out. They have thinner atmospheres, which means less light is absorbed, which means you have thinner spectral lines. Small stars have thicker atmospheres, and so they have thicker absorption lines because they absorb more light. Please write this down. Small stars, thicker absorption lines. Big stars, thinner absorption lines. If I've repeated myself this many times, you're going to see it on a test. So is there any way to tell which star is the biggest if you see something like this? Any way at all? This next guy definitely does not have my favorite voice, but he goes over what we just talked about. He also answers today's question of the day.
Stars of a particular photospheric temperature can have vastly different sizes and luminosities in an HR diagram. For example, at a temperature of about 3000 Kelvin, there's Proxima Centauri, a low-mass main sequence star, only 3% the size of the Sun, Aldebaran, a red giant that's 20 times larger than the Sun, and Betelgeuse, a red supergiant 1,000 times the Sun's size. Yet spectroscopy alone can distinguish between these situations. This is because spectral lines reveal the diffuse nature of the atmosphere. In the more diffuse atmospheres of the larger stars, there are fewer collisions, and the lines are narrower. In the denser atmospheres of the smaller stars, there are more collisions, and the lines are broader. So line broadening gives an information about luminosity class, and astronomers can distinguish between main sequence stars, giants, and supergiants.
Now that we know how we give them the numbers, let's take a look at these. Hypergiants, the biggest of 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 the biggest stars that exist. Hypergiants are the biggest stars. They have a luminosity class of 0, which is technically not a Roman numeral. So the biggest of the big stars, a hypergiant, Roman numeral 0. Hypergiants are going to be up here at the top of the HR diagram because they are the brightest star, so the luminosity is going to be the biggest. Why are they the brightest? Because they are incredibly huge. They're the biggest. They have the most surface area. They are incredibly huge, which means they burn through their fuel incredibly fast. These are the stars that only last about 1 million years. Our sun's going to last about 10 billion. These last about 1 million. Put that in perspective. If our sun was an average person and they were 70 years old, most people live a little bit longer than that now, but let's just, for easy math, say that our sun was a 70-year-old human. That's the 10 billion year lifespan. How long would these stars last? About 2 weeks. So if our sun lasts 70 years, A hypergiant would last about 2 weeks. Needless to say, we're probably not going to find life around one of these stars. They just aren't around long enough. We've talked about some of these stars. They're the biggest of the biggest of the big. VY Canis Majoris was one. NML Cygni was one. There was a star called Westerland that was named after the guy who found it. And now, right now, currently, the biggest star is UI Scuti. These are the rarest of the rare stars. The biggest of the biggest of the big stars. Go ahead and write down an example of a hypergiant. And here is some of the information that you guys can write down in your little chart. Supergiants. Still a giant star. Still in the end stages of its life. These have a Roman numeral of 1. 1A and 1B. Still very massive, very luminous, extraordinarily bright, has a very short lifespan. These are very rare. Supergiants are more common than hypergiants, but they're still less than 1 in a million. There's a ton of stars out there, which means there are still a ton of supergiants, but they are extraordinarily rare. Here's a couple examples. We have Canopus, Betelgeuse, Rigel, and Antares. These stars, just like hypergiants, because they are classified as giants, mean that they are about to die. They are in the end stages of their life. They're no longer on the main sequence. People ask the difference between 1A and 1B. That's literally just the size. So 1A is going to be a little bit bigger than 1B. Rigel is putting out a little bit more light than Antares and Betelgeuse. And Rigel is smaller, but Rigel is hotter, which means it's going to be putting out more photons, more energy. So the luminosity is a little bit bigger. So the luminosity of Rigel is 1A, Betelgeuse and Antares 1B. Just to see how big these are, this is Betelgeuse and Antares, and our sun is 1 pixel big. So they're large. Giants, numbers 2 and 3. This is what our sun's going to turn into. Our sun is not big enough to turn into a supergiant or a hypergiant. Our sun's simply going to turn into a giant, a red giant. So these are low mass stars, stars like our sun, at the end of their life. So once they've moved off of the main sequence and they're doing the stuff that they're going to do right before they die, we'll get to that tomorrow, then we classify them as giants. I also want to point out that if you are a huge star, as you start expanding, you're going to pass through this section on your way to the supergiant or the hypergiant section. So if you're a big star on the main sequence and you are starting to die and you start expanding out, well, you're going to pass through the giant phase on your way to supergiant phase or hypergiant phase. A couple examples: Arcturus, Aldebaran. Go ahead and write some of these down. Subgiants are the stars who have just moved off of the main sequence. So when our sun runs out of hydrogen and starts burning, fusing helium to make things like carbon, it's going to start to expand. Right when it starts to do that, it's going to expand out. It's going to be known as a subgiant. It's not to its full red giant phase yet. It's on its way. It's between main sequence and red giant. So subgiants are stars that are currently growing in size, and this does take millions and millions of years, so it's not like it's this way for a month. It takes a long time. But these are stars that are currently moving off of the main sequence and turning into big giant stars. An example is actually Procyon, which is just entering this category. So it would be an F5 4-5 because it's halfway in between a main sequence, which is 5, and a subgiant. So it's currently growing from main sequence size to giant size, and it's going through this subgiant phase. Now we're to the dwarf stars, and you might think, wait a minute, our sun's not small. That's just the naming system that they have. If you are a main sequence star, you are considered a dwarf star. So our sun is what's known as a yellow dwarf. Why? It's classified as a yellow star, and it is a main sequence star, so it's a yellow dwarf. If you're on the main sequence and you're blue, you're a blue dwarf. If you're on the main sequence and you're red, you're a red dwarf. So a main sequence star is just any normal hydrogen-burning stars. Hydrogen fusion is going on in the core. You're doing your normal star stuff. You're going to be doing this for like 90% of your life. You just kind of sit on the main sequence for a very, very long time. If you're a main sequence star and you're the biggest of the big, you're a class O star. You're absolutely enormous. You might actually be putting out more photons, more energy than the sun will as a red giant. So there are some dwarf stars, main sequence stars, that can put out more energy than a red giant star. A couple examples are the sun and Sirius, the brightest star in the night sky, and Vega, which is the 0 point for our apparent magnitude scale. Now we've looked at hypergiants, which are zeros, supergiants, which are 1, giants, 2 and 3. Subgiants are 4. Those are the ones that are on their way to becoming a giant. Main sequence is 5. And we're going to skip down to white dwarfs, which is 7. Where's 6? Why is 6 not on? 6 is actually not put on most HR diagrams. 6 is what is known as a subdwarf. And most HR diagrams are simply going to lump subdwarfs in with main sequence stars. Let me show you why. A subdwarf is a main sequence star. A subdwarf is a main sequence star. A subdwarf is doing regular star stuff. It is burning hydrogen, turning it into helium. A subdwarf is a main sequence star. So it should just be on the main sequence. However, every single time we plot actual stars, we get this little group of stars that's down here under the main sequence. And they are burning hydrogen. So why are these stars down here underneath the main sequence? Turns out these are like generation 3, 4, 5, 6 stars. Remember, generations of stars, generation 1 was the first stars to ever exist. They fused heavier elements in their cores and then exploded. And the second generation took those guts, so there was already some heavy elements in them. And then they made more heavy elements and exploded. And then the third generation took all of those heavy elements as they were being formed. We think our sun is a third generation star. When a big third generation star dies, it's going to explode out even more heavy elements. So as generations go, you get a buildup of heavy elements. Things like carbon, oxygen, nitrogen, all the way up to lead. And if it's supernova, you get things past that. As far as astronomy is concerned, everything that's not hydrogen and helium is known as a metal. Has nothing to do with the periodic table. It's just, is it hydrogen or helium? If the answer is no, we call it a metal. So carbon would be a metal. Oxygen is a metal. Nitrogen is a metal. If you are a star and you have what's known as a high metallicity, you have a lot of these already big elements in you, you're not going to burn as bright. You're not going to put out quite as much energy. And so when they are plotted on an HR diagram, even though they are just burning hydrogen, turning it into helium, they're not as bright because they've got so many heavy elements already in them. And they form this little subdwarf category. And so they gave it a Roman numeral, 6. But because they are burning hydrogen, turning it into helium, doing main sequence stuff, it's usually lumped into the main sequence. But there is a category, number 6, called a subdwarf, that are not quite as bright as a regular main sequence star. And now let's talk about a couple other types of dwarfs. Our sun is a yellow dwarf. Red dwarfs are main sequence stars that are very tiny. White dwarfs. A white dwarf is how our sun is going to die. A white dwarf is a very, very tiny object that is the leftover core of a star. They're made up of what's known as electron degenerate matter, which we'll get to in just a second. And they're basically the leftover core. Once fusion has stopped, whatever's left over, that is a white dwarf. They're extraordinarily dense. They are very compacted together, where a teaspoon of a white dwarf star, just a teaspoon of a white dwarf star is going to weigh the same as an elephant. So they are very dense, much denser than anything on planet Earth. And the reason that we can see them is because, being the core of a star, they are extraordinarily hot. And so they are glowing with blackbody radiation. It's not light produced with fusion, it's leftover heat energy that's being radiated out. And because they are so hot, that heat energy that's being radiated out is in X-rays. So we actually didn't see them until we started looking out with X-ray telescopes. They are going to slowly just cool down. There's no fusion happening in the core anymore. It ran out of hydrogen. So what's happening is that heat is radiating out, and it will slowly cool down. Very slowly, though. It will take roughly that many years. I don't know what that is called, but that is a long time for these white dwarfs to slowly cool down. When a white dwarf cools down so that it's the same temperature as outer space, it will now be called a black dwarf. So a black dwarf is nothing more than the cooled down core of an old star that's being held up by electron degenerate matter. What is electron degenerate matter? If you remember, fusion in a star is pushing out against gravity, right? So gravity is pulling in, fusion's pushing out, and there's a balance. Once fusion turns off, gravity starts to win, and gravity starts pulling down, and it will keep pulling and pulling down and smushing those little particles together until eventually it tries to take one atom and push it into another atom. The problem is that atom has an electron, this atom has an electron, and what do two negatives do? They push apart. So if I have one atom and I try to push it into another atom, the electrons are going to be what starts pushing back against gravity. That's electron degenerate matter. It has degenerated all the way down and pushed together until the electrons themselves are what's pushing back against gravity. It's not fusion. It's now the electromagnetic force. The two negative electrons are pushing back out. So a very, very dense object, the leftover core of a star, is a white dwarf. And it will take this many years in order for that white dwarf to cool down. Cool story, the universe is only 13 billion years old. So there is not a single white dwarf anywhere in existence in the entire universe that has cooled down into a black dwarf, which means those don't exist yet. They will in the future, way in the future. But because the universe is not old enough for a white dwarf to have existed and then cooled down, black dwarfs are hypothetical. Right now we've got white dwarfs. We can calculate how long it will take for them to cool down, and that length is longer than the age of the universe, which means black dwarfs don't exist yet. And now there's a couple other categories. There are some objects that sometimes fit our classification scheme and sometimes don't. There are these things called brown dwarfs. A brown dwarf is an object that's too big to be a planet, too small to be a star. So if you go in between like the size of Jupiter and the size of a red dwarf, that is going to be an object of a size that we don't know what to call it. They're not big enough to do fusion, which means fusion is not happening in the core of that object. Obviously, it can't be a star, right? If they're not big enough to do fusion, you can't classify them as a star. But they're still big enough that the gravity is pushing things together enough that it causes the core to heat up. Not enough for fusion, but that heat will radiate out, and we can actually detect these objects because they are radiating out electromagnetic waves. They're radiating out light. So they're not quite as bright as a star. They're not doing fusion, but they're huge objects who are so big that their gravity is causing them to heat up and glow. Planets don't do that. Planets don't glow. These brown dwarfs do because they're so big. So we have a number of different objects on the screen right now. We have the Sun, an M-class red dwarf star. We've got Jupiter, and in between this Jupiter is a little bit bigger than it normally would be. In between a red dwarf star and a planet, you get brown dwarfs. Brown dwarfs are not doing hydrogen fusion, but they are big enough to put out heat and glow, and we can actually see them. Most astronomers consider them stars, or a type of star, or a subcategory of star, because they are glowing. So we've got an M-class star, and then an L-class star, a T-class star. The surface temperature is up to about almost 2,000 degrees. And then a Y-class.
Teacher, please pardon the interruption. There's a couple things going on that I...
And then we have these Y-class stars, and these can be plotted on an HR diagram, are considered stars by many astronomers, and the outer temperatures can be the same size as like a human body, 100 degrees Fahrenheit. If you could go to these stars and not sink, you could actually stand on the surface of these stars and not burn up. Imagine standing on the surface of a star and not burning. And you could do that with some of these brown dwarf stars. Once we realized that brown dwarfs are radiating out light in the infrared, and we started looking for them, brown dwarfs are everywhere. This is a photograph of a little tiny section of the night sky, and the sun is there for brightness comparison. The brown dwarfs are the circled objects. The stars are bright, and brown dwarfs have to be circled because they are radiating out in infrared. You can't see them in visible light, at least not this far away, but you can see them with infrared telescopes, and they are everywhere. They are just as numerous as stars are. So what is a brown dwarf? A giant object out in space giving off light. Most people call that a star. Into